It's on the 8th. Espera, ahora, por favor. It's on the 8th to the 15th, and we have to go
Yeah, I
there
believe so.
physically.
Yeah,
Okay,
I believe
so it's a whole week. It's a whole
Yeah.
week. Okay, okay,
Yeah.
okay. Okay.
Let me know soon, okay?
Mhm.
All right. So let me, oh, we have Patrick too, good. Okay, let's start with this. Are you able to see this? The full screen version?
Not right now. It's kind of like frozen.
Okay.
What email were they talking about? Because I don't think I've received an email from you.
Yeah, no, I sent them something else. This was about a different opportunity for them.
Okay, I see the
Are you
screen.
able to see this now? Okay,
Yeah.
good. And you see the full screen, right?
Yeah.
Okay. All right. So let's talk about connectivity, and from there we'll go to biconnectivity. Now, connectivity we all kind of understand. Let's see. So here's a graph that has 1, 2, 3, 4, 5, 6, 7, 8 different vertices, a bunch of edges shown in red. And it's clear just by looking at it that it's not connected. And the reason it's not connected is because you can't get from anywhere to any, well, you can't get from some vertex to every other vertex. For instance, you cannot get from 4 to 8 because there are no edges that cut across. So this graph here is not connected. On the other hand, this second graph that I'm just showing you here on the right-hand side is a connected graph. Here we have a couple extra edges between 2 and 4 and between 1 and 8. And now you can get from anywhere to anywhere. Of course, both of these are undirected graphs. And we know how to test for connectivity because all we have to do is to run depth first search or breadth first search. In the graph on the left, it doesn't matter where you start. If you start somewhere here, you'll finish with depth first search or at least one round of depth first search and visit only one connected component. And so you would never get to vertex 1 or vertex 8 if you start depth first search somewhere here. Same thing if you start somewhere here, you're never going to get to one of these vertices. So by doing depth first search, if we don't visit every vertex, then we know that the graph is not connected. Whereas the one on the right side here, it doesn't matter where you start depth first search, eventually you're going to get to every other vertex. And so therefore, this graph here is connected. So this much we learned from several weeks ago, and you guys are comfortable with this concept. So I told you a little bit about biconnectivity last time. So let me see what I can tell you more. So the things, the bullets on the left talk about connectivity, the bullets on the right talk about biconnectivity. Now let's see how they're different. A graph is connected if there exists a path between every pair of vertices. It doesn't matter which pair you pick, you should be able to go from one vertex to another. Such a graph, at least in the undirected case, is called connected. What's biconnectivity? A graph is biconnected if there exists two disjoint paths between every pair of vertices. Now, these two paths cannot intersect. They cannot touch on any vertex. So in some sense, connectivity simply requires that you find one path between a pair of vertices. Here it says for any pair of vertices, you need to find two disjoint paths. Does that make sense? Everyone understand this definition?
Makes sense to me.
Okay.
Yeah.
Now, if you have, what's really interesting or useful to know is that if you have two paths from a vertex to some other vertex, then essentially you form a cycle, because you can take one disjoint path to get there, and you can take the other path to return back. So therefore, every vertex is on some cycle. And in fact, it's on a cycle with every other vertex, because you have two different paths. So if you take vertex A and vertex B, and it doesn't matter which ones they are, we know that if it's biconnected, you have two distinct paths, and you can take one path to get from A to B and the other path to get back from B to A. So that means it doesn't matter which pair of vertices you pick, they are going to be on a cycle. Now, I'm going to tell you about something called minimal connectivity. A graph is called minimally connected if you remove either an edge or a vertex from the graph and it's not connected anymore. Such a minimally connected graph must be a tree, because if you have any cycles in the graph, then you can remove one of the edges without harming connectivity. So if you have a cycle, all you have to do is to remove one edge. You will still be able to get from anywhere to anywhere, because you can take the other part of the cycle. But it only allows you to take off one vertex or one edge, and you'll still have connectivity between the rest. Does that make sense? That's for the connectivity. Now, the same definition for biconnectivity is that a graph is minimally biconnected if by removing any vertex or an edge, it's not biconnected anymore. So that's called a minimal biconnectivity. Here, such a minimal connected graph is called a tree, and here the minimal biconnected graph is a cycle. And remember, here it's a cycle with no other edges, because if you had any other edges, you could just remove that and it won't hurt the biconnectivity. If you have a simple cycle, if every vertex, if all the vertices simply sit on one big cycle, then this graph is already biconnected, because between every pair of vertices, it doesn't matter which two vertices you pick on the cycle, you can get from A to B using two different paths, one using the top part of the cycle and the other using the bottom part of the cycle. Does that make sense? So a cycle is a simple example of a biconnected graph. And in fact, it's the minimal one, because if you remove even one edge, the cycle is not going to be biconnected. Same thing with a tree. A tree is simply connected, because that's our definition. But if you remove any edge from the tree, the graph will not be connected anymore. So that's your comparison between connectivity and biconnectivity. Now, in a connected graph, you have to remove at least one vertex or edge in order to break it apart. In a biconnected graph, you have to remove at least two vertices or edges in order to disconnect, in order to break up the graph. And that's the way this definition compares with each other. So these are the two concepts that we are going to explore a little bit more and see how it's useful and what we can do with it. Any questions about this?
No, all good.
Okay, all good. Well, we also need a couple more definitions. For the connected case, we talked about connected components. And if you recall, a connected component is a piece of the graph where You can get from anywhere to anywhere within that component. A bi-connected component is the same thing. It's a piece of the graph where that piece is bi-connected. And if you add anything more to it, it will not be bi-connected anymore. So such a piece is called a bi-connected component. So let's go back to our example here. Let's look at the second example. We know that this is a connected graph. First we had this example, which was not connected. Here the connected components are, this is one component, this is one component, and this is one component. Now, this one here is already connected, but is it bi-connected, you think?
No,
No.
Why not?
because if we start at 7 and we wanted to go from 7 to 1, we can
Yeah.
only take one path. We can't take two.
Well, there is a second path. I could go this way.
Oh yeah,
I could go this way.
but you repeat the same vertex and edge.
That's right. It's not two disjoint paths.
Yeah.
Because every path will need to use this edge, right?
Yeah.
Because of that, you're never going to be able to find two disjoint paths. All right. Intuitively, we understood this, but now if you apply the definition, it starts to become clear. So therefore, this graph here is not bi-connected, but it's connected. So bi-connectivity sort of takes you to the next level. Now, the next question is, what are the bi-connected components of this graph? And it turns out that we already know that a cycle is bi-connected, right? So this guy here, 4, 5, 6, 7 is a bi-connected component. Same thing with 1, 2, and 3. It's also a cycle, and it's also a bi-connected component. It turns out that these are your two non-trivial bi-connected components. We also throw in this simple edge, this edge and this edge, as extra bi-connected components. By definition, they are bi-connected components, even though it's true that you won't find two paths from 4 to 2. So this is by default, we're going to call it bi-connected. It doesn't quite follow the definition, but it does follow a different definition. That different definition says, if I remove only one vertex, the graph is still connected. And if you just have an edge, and if you remove one of the vertices, it's still going to be connected because there's only one vertex left, and that one vertex is connected. So sort of by default, it's called a bi-connected component, even though it's not one in the strict sense of the term.
Wait, can you repeat in this graph, can you repeat the subgraphs that are bi-connected?
Right. So it turns out that this here is a bi-connected component. This here is a bi-connected component. So is just an edge and just this edge. So what you see is that some of the vertices get repeated in the bi-connected components. So 4 is part of this bi-connected component as well as that bi-connected component. Does that make sense?
Okay.
So it turns out that bi-connected components are a collection of edges, not a collection of vertices. So for instance, if I were to, let's see if I can color this. Yeah, if I use these colors, what you'll see is that this here is one connected component. It's these 4 vertices and the 4 edges. And let me change the color. The second connected component, second bi-connected component is simply this edge. And then the third bi-connected component is the triangle. I'm not going to color it, but it's just this triangle here. Well, I might as well do it. So that's number 3, and number 4 is this guy. Those are your connected components, and you see that they're not totally disjoint. They share some vertices sometimes, but that's okay.
So every bridge is a biconnected component?
Every bridge is a biconnected component by itself. That's just a default definition. It's not a perfect definition. Make sense?
Yeah.
Okay, great. So let's get rid of this here. Oh, I should have cleared it. Okay. All right. So let's continue with the definition. So now we have kind of clearly defined what's a connected component and what's a biconnected component. And what I told you was that there were a couple of these degenerate cases. The degenerate case for the connected component is just one vertex, because one vertex by itself is already connected. If it's not connected to anything else, it's still okay. It's still a connected component. In the biconnected component case, it's just a simple edge that's also going to be a biconnected component. All right. So let's move forward. Oh yeah, there is a second bullet here. It says, if a graph is not connected, you can decompose it into the connected components. So every vertex in the graph will belong to one connected component. And the corresponding definition for biconnectivity is that if the graph is not biconnected, then you can break it down into biconnected components where some vertices may be part of multiple biconnected components, but every edge is going to be part of only one. Okay?
Wait, I have another question.
Yeah.
I'm sorry, this
No
is pretty
problem.
similar.
Yeah. No, this is actually quite tricky, so you should ask questions.
So if we have a single vertex and 0 edges, would that graph be a biconnected component? Or would that have 0?
So we would call that biconnected by default. You're right.
Okay.
So default ones would be just a single vertex by itself or a single edge by itself. Now, in general, we're going to be interested in biconnected components only if the graph is already connected. Otherwise, it's not as interesting. So if you're given a graph, the first thing we would do is to find all its connected components. Then for each of the connected components, we'll go and find its biconnected components. So that's why this other case is sort of not going to be so relevant for us. But I guess you're right. There could be a single vertex by itself. All right. So any more questions before I move on? Okay. Let me go back to. Okay. So let's assume that here's a graph, and you have 1, 3, 3, 6, 6 and 4, 10. So there are about 13 vertices here, bunch of edges. And the question is, what does depth first search do for you? So remember, what I'm doing now is to setting up the stage for figuring out testing for biconnectivity. And second thing is, how do I find all the biconnected components? That's what I'm going to talk about next. So, all of this is going to be based on depth first search, which you're already familiar with. And I'm going to show you what happens when you do depth first search on this particular graph. We're going to use this as an example here. So over here, depending on where you start, you're going to get a different depth first search. And I think I have an example worked out here. It turns out I'm going to start with A and work my way in this manner. I'm going to go from A to F, F to E, E to G, G to L, and so on and so forth. So you can see the numbering here: 1, 2, 3, 4, 5, 6, 7, and then I walk back and go to 8. Then I walk back and go to 9 and 10 from 4. Then walk back and then go from 4 to 11. Then walk back and go to 12. And then I walk back all the way to A before I find B. So the order in which the vertices are going to be found are given by this number here, which is pretty much what the code that we wrote last time. The numbers may be off by a little bit from if you apply the code, but at least the ordering is going to be exactly the same. Now, what I've shown you here in green are called the back edges. These are the edges that were not used to find new vertices. So the thick black edges were the edges that were used to go find your next new vertex. And the green edges are the edges that were you discovered. When you discovered them, the other end of the edge was already discovered, and that's why we call it a back edge, because it leads to something that's a lower numbered vertex. So there's a green edge from 4 to 1, or there's one from 6 to 4, or from 8 to 5, or from 11 to 1, etc., etc. Oh, yes, Clement.
So would those back edges kind of help us to find our cycles for the bi-connected components?
That's what we are going to look at. That's right. Remember, in bi-connected components, we don't necessarily want to find the cycles. All we want to do is to find bi-connected components, or we want to see if the graph is bi-connected.
Okay.
So let's start with the simple case. How do I figure out if the graph is bi-connected? So what would be your first step? So let me give you go ahead.
Like, wouldn't we try to find two distinct paths between two vertices and stuff? Like two disjoint paths using depth first search, or would we not do that? Or am I getting something wrong?
Well, so let's make sure we understand the definition of bi-connected graph. I'm asking the question, this graph that I'm showing you here, is it bi-connected or not? And we can stare at it and convince ourselves that it is or it is not bi-connected. That doesn't matter. But let's make sure we understand the definition. Do you remember the definition from a couple slides ago?
Has two disjoint
Good. So you remember the phrase two disjoint paths. But tell me more. What did we say? Did we do this for specific vertices, all pairs of vertices? What did we say?
pairs of vertices? No.
Not clear enough. You have to be mathematically precise. Otherwise, your algorithm is going to go for a toss.
Okay.
Anyone remember the definition?
It's for it's
So
for
let's talk about connectivity. What's the definition for connectivity? When do we call a graph to be connected?
When starting at one vertex, we can visit every other vertex. And there's a path from one vertex to every other vertex in the graph.
There's at least one path.
Yeah.
At least one path. Okay, that definition works. Another definition is that between every pair of vertices, there is at least one path. Fine?
Yeah.
Yeah.
So it turns out that both these definitions are equivalent. It doesn't matter which one you use. Now, what is key there is that we, at least our second definition said, for every pair of vertices, there is at least one path. So the key phrase there is for every pair of vertices. The definition for biconnectivity is exactly the same, except that you have to replace 1 with 2. So what's the definition for biconnectivity? The equivalent definition is, what is it going to be?
There is
Okay.
at least 2 or more disjoint paths for every pair of vertices.
For every pair of vertices. So make sure you repeat that phrase for yourself. For every pair of vertices, you have to make sure that there are at least 2 disjoint paths.
Okay.
Now, how can I test this using depth first search? Let's just forget about every pair. Let's just try and do this for one pair. Let's say that I pick A and E. And I want to know whether A and E, there are 2 disjoint paths connecting them. So in order to check this, it turns out it's not that trivial. Because depth first search only will help you to get there. It's unclear how you find that second disjoint path, because if you pick one of the paths, it might prevent you from taking some other path because that may not be disjoint for you. Okay.
What the way would be like to like prove it if it's a cycle?
Sorry, say that again.
Like I remember with the code for depth first search, you had like some code that that would like help to prove that it was in a cycle or something like that. Like, would that also help too?
Yeah, no, that's not going to help you. So this is why this needs a very, very different thinking. And I just want you I just wanted to make sure that you understand the definition and the challenges that the definition poses. So the main challenge with the definition seems to be, firstly, even to check whether given a pair of vertices that there are 2 disjoint paths. And then we need to do this darn thing for every pair of vertices. Okay, so the definition makes it really difficult, really challenging to check whether the graph is biconnected. Now it turns out, sorry?
Yeah, can I
go ahead.
Can I ask something? Okay.
Yeah, of course.
So this is just an assumption to see if there's 2 disjoint paths. We start off with one vertex. So let's say we start off with A, and let's say our target is E. So we do depth first search on A until we reach to E. Once we reach our target, we do depth first search on our target and try to take back edges to A.
All right. So you've done just this part of the depth first search, A through E. Mm-hmm. And now you're starting depth first search from E all over again, it seems. Mm-hmm. And now I don't know whether, since I'm starting all over again, I don't know which edges are back edges and which edges are going to be tree edges for the original search. So what do I do?
Wait, can you repeat that again? Okay, so wait, actually.
So I've started at A, and here is where I reach E. So I have this as my tree edges, right? These big fat edges are the tree edges. Mm-hmm. Now I need to find a path back that uses back edges, but I don't even see a back edge going off from here.
So if we don't see a back edge, then we continue going down, and now we visit G, and we check if G has a back edge.
Right. So essentially what you're doing is you're not doing depth first search all over again from E, you're just continuing your depth first search from E.
Yeah, pretty much, yeah.
Right?
Yeah.
So we might as well say that we're just going to do one depth first search from A and try and figure something out. But your general intuition is correct, because this back edge will do it for us, right? Because this back edge will mean that there is a bunch of tree edges that will get from A to G, and then you'll use this back edge to go back, and on that path is E. Mm-hmm. So if some descendant of E is ever able to go back all the way to A, then you're done.
Okay. that makes
So
sense.
it could be G.
Mhm.
In this case, that worked. But let's say this edge were not here. Would it still work out?
Oh,
Yes, because C goes to A.
yeah.
That's right. So there is some other descendant from which you could go up to A. So I have to go and search all the descendants of E and see if it has some back edge that goes to A. Now the problem is that I could mess you up by saying, what if this edge is missing, okay, going from G to A? And what if my edge goes from, instead of going
Oh,
all the way to A, it goes halfway. Let's say it goes to, I'd have to find you a different example. Hold on a second. Yeah, let's say that I ask you a question about G and J. Forget about A and E. I'm
Okay.
asking you a question about G and J is somewhat easy. I need a better example. Hold on.
can we just add another vertex, call it N?
Yeah.
Or and then just add it
Yeah,
to...
I can, but I'd have to draw it over here. So I'm trying to see if there's a simpler way to do it. Give me just a minute.
Okay.
Yeah. So you're right. Let's add a new vertex in between L and J.
Okay.
Okay. Now we ask the question: Is G and N? Oh, but this also has an easy solution. Dang. Let's draw a different one.
Wait, are you trying to say that we might have to take multiple back edges to get to A?
Yeah.
Oh, okay, I see.
Yeah. And I'll show you an example. Raw. All right, let's draw it here, see what happens. So let's say I did depth first search, okay? And let me draw a bunch of vertices. They're not going to look pretty, I'm sorry about that. So let's say these are my vertices. And let's now go to the tree edges. These are the fat tree edges, and it's all a straight line. Fine?
Yeah.
Depth first search just went 1, 2, 3, 4, 5, 6, 7. And along the way, let's assume that, by the way, if you have this as your entire graph, is it biconnected?
No.
It's not.
Yeah.
And why is that? Well, it's obvious because there's only one path from anywhere to anywhere. All right, so let's draw some back edges, and let's draw that in, say, blue. So here are some back edges. So now, is this graph biconnected?
Yeah, a subgraph of it is biconnected.
Well, that's not what I'm asking. Is this graph
Oh.
biconnected?
No.
No.
Again, no. Why? Because, okay, we can number them 1, 2, 3, 4, 5, 6, 7. There are no two disjoint paths from 7 to 1 or 7 to 2, right?
Yeah. Yeah.
Okay.
Mhm.
Okay. So, so this doesn't cut it. Now, if I make a blue edge from here to here, is it now biconnected?
Yeah.
Why is that? Well, it's obvious. It's
cycle.
intuitive. Even if you don't have this edge, right?
Yeah.
All these vertices are on a cycle, and that's good enough.
Yeah.
That already makes it biconnected. So let's not do that. Let's instead make the edge go from here to say here. Is this biconnected?
Yes.
Yes.
You sure?
Yes.
I'm gonna stay with my answer.
Yeah, me too.
No, I'm not. I'm not. I'm not going to this thing.
It's like an investment. Maybe I'm right.
Hold on. Let me try to prove no before I say yes.
All right, you got 30 seconds.
Okay.
While I munch on my.
You're wrong, Clement. Admit it.
No, man. I'm gonna have. Okay, I'm gonna have to go with yes.
Couldn't find a counterexample, huh?
Yeah.
Okay. Well, it turns out all your hunches were right. This is biconnected. Now, well, how do we prove this? It's unclear. Or let me give you another example. What if I remove this guy here? And what if I instead add this guy? Is it biconnected?
No.
You're sure?
No.
Why is that?
We repeat a vertex.
So what?
We
Wait.
can't do that, no? That if we were trying to get to the second to last vertex, no matter what we
Yeah.
do, we would have to repeat the vertex
No,
where
wait.
those two
Yeah,
back edges meet.
it's biconnected.
Wait, David has changed his mind. He's calling this biconnected.
Yeah, I'm calling it biconnected.
Are we going off of vertices or edges? Isn't it vertices and edges?
Oh, no, this is.
You can go
this is
from that
biconnected.
blue. You can go from that blue edge and go to the other blue edge.
Yeah,
Well,
yeah.
let me number these
Cycle,
just
though,
for
so
your.
that's why it's
So
biconnected.
this is 1, 2.
Dude, there's no way. Okay, let's say we want to get here, right? We can take this path here, right? Or we can take this one. Oh, let me choose a different color. Or we
Yeah,
can take
go
this
ahead.
one and then go around and then back in. But we're repeating this vertex. Isn't it that we cannot repeat vertexes? Or is
That's
it
right.
only off? So it's not
Disjoint. It has to be disjoint.
Yeah.
But
I
isn't
really
it a cycle though?
You have to go back to the definition. You cannot work with half definitions. So the original definition says between any pair of vertices, you need to have, what's the definition again?
2 or more disjoint.
You're just
Two or more disjoint paths. You need at least 2 disjoint paths. Now, what Lazaro is saying is, let's take 2 and 6. How are you going to make 2 disjoint paths from 2 to 6? Okay, from 2 you could go, you could send 2 guys in different directions, right? However, their paths has to go through 5 if it ever has to go to 6. So that's going to make it not disjoint.
Yeah.
Another way to think about this is what we discussed last time. You remember what we talked about? These articulation points?
Yeah, yeah,
Remember that?
yeah.
Now, are there articulation points here? Or
Yeah.
should I repeat the definition for some of you?
There are
Anyone-
articulation points. Well, except the last few at the ends.
No.
There are also articulation points.
Hold on a second. Let me make sure everyone knows the definition. Is there anyone who doesn't know the definition of an articulation point?
It is not fresh in my head right now.
Not fresh in your head. Okay, no problem. An articulation point is a vertex whose removal will disconnect the graph. It'll break it into two.
Okay.
Is there such a vertex here?
Mm,
Vertex. If you remove vertex 5,
5, yeah.
That's right.
yeah.
If you remove vertex 5, you're going to be in trouble. It'll break the graph. Therefore, by one of our other definitions, it's not biconnected because I can disconnect it with just one vertex removal.
No,
Got it?
got it.
So this is why it's useful to know your definitions and useful to know them precisely. One
So-
definition. Go ahead, David.
Okay, yeah. So biconnected, even though there's another disjoint set of edges to get from say 1 to 7, right? You just take the blue
Disjoint-
ones.
Disjoint set of edges is different from disjoint set of vertices.
Oh, okay. You need both.
You need
Oh,
both.
okay.
Well, if you have disjoint set of vertices, you're automatically going to have disjoint set of edges.
All right. Yeah.
So I only need to worry about vertices. Clear?
Yeah.
Clear.
So it turns out that an alternative definition of biconnectivity is that there are no articulation points. And what's an articulation point? An articulation point is one of those critical vertices whose removal breaks the graph.
Yeah.
So all of these concepts are connected, it turns out. So I'm going to remove this. Are you now clear about what we were saying? So maybe I should do this one more time. So remember, I showed you this thing where, right. So let's say that I still have this edge, okay? And we know it's not biconnected, but let's say I add this guy here. Is it biconnected?
Mm,
More complicated, right? Not so easy to verify.
Wait, yeah, it is biconnected.
So it turns out now that 5 is not an articulation point anymore because you try removing this, what happens? Well, it's still going to hang off of this edge.
Yeah.
yeah.
So you're not disconnecting the graph. So therefore, this is biconnected.
And those
Now-
blue lines will represent a back edge, right?
They're all back edges.
Okay.
The black lines are the only three
Three
edges.
edges. Okay.
Okay. Now, what did we learn from this? So if my question had been about, let's say, 2 and 4, and I asked you the question, are there 2 disjoint paths from 2 to 4? Well, you're going to say, okay, I'm going to do depth first search from here, right?
Mhm.
And I don't know, it will have some strange appearance, but it's unclear how I'm going to figure out whether. So actually, let's do this. Let's see what the depth first search from 2 is going to look like. So this is 2, and then from 2 I would go to 3, right?
Mhm.
Sorry, let me erase this. Good. Okay, here's 3. We're going to number it the way it was before. Okay, so bear with me. Something happened to number 2, but that's okay. From 2, let's say I go to 3. From 3, let's say I go to 4. From 4, let's say I go to 5. And from 5, let's say I go to 6. From 6, let's say I go to 7. So these are my black edges. but I still haven't finished my depth first search because I haven't visited one. The question is, where will one be? Anyone wants to help me? So then, so this is 2, 3, 4, 5, 6, 7. I will see this back edge. I will see this back edge, but this edge will not be a back edge anymore. Does that make sense?
Okay, why?
So let me number them so that it's all clear to you. So here is 2. Here is.
Oh, because
here
we're
is
going.
3.
Is it because we're starting from 2?
Yeah.
We haven't visited 1 yet.
Remember, now I'm asking the question: are there 2 disjoint paths from 2 to 4? So based on your idea, what we're going to do is to do depth first search from 2, and then we're going to try and figure this out, right?
Mhm.
Right.
So let's go and do this. So we've got, we started from 2, and this is what we've done so far. At 7, we're going to see this back edge to 5, right? And, oh, hold on. So we're going to see this package from, oh, not. We're going to see this package, 7 to 5, and we're done. We go back. At 6, we're going to see this package from 6 to 3, and we're done. Then we go back to 5, and we see an edge to 1, and 1 has not yet been seen. So what's going to happen? 1 is going to be a new vertex that you're going to encounter. Okay, and let's draw that here. There's going to be a black edge going from 5 to 1. That's
Oh,
what
that
your
makes
depth first search.
sense.
Okay, so your depth first search is going to look very different now.
Yeah.
Now, are we missing an edge somewhere?
Yes.
What are we missing?
1 to 2.
1 to 2. So 1 to 2.
Oh my
That's
god,
going to
it's
be
a
now a
back
back
edge.
edge.
Yes.
Okay. So what does this tell us? I know I numbered them differently. The depth first search numbering would be very different now. In fact, it would be 1, 2, 3, 4, 5, 6, and this would be 7. But that's okay. This is so that we can connect it to what we have here. So if we were to start from 2, this is what it's going to look like. Now we ask the question, are there 2 disjoint paths from 2 to 4? And remember the discussion we had before. This was actually Lazaro's idea, saying if from 4 there is some back edge that will help us to get there, well, that would do it, right?
Yeah.
So what if I asked you about 2 and 6? You would still do the same depth first search, right?
Mm-hmm.
Now, how do I figure out that there are 2 disjoint paths from 2 to 6?
There isn't.
You just told me that the graph is biconnected, so there must be. Because if it's not, if there aren't, then there must be an articulation point, because it's not,
yeah.
it's not
Yeah.
biconnected.
Yeah.
But there isn't one. So you better be able to find 2 different paths from 2 to 6, or else we are in trouble.
Yeah, well, you can do it. You go from 2 to 1.
Very good.
Then
Yeah.
you can go from 2 to 3. Then you get 6 with the back edge.
Right. So what you can see now, based on what Adriana just said, it gets horribly complicated.
Yeah.
Okay. And in general, it could be a big freaking mess. There's trying to find that cycle is going to be very, very challenging. So instead, we're going to rely on the theory and simply say, hey, 2 and 6 are in the same biconnected component because the whole thing is biconnected. So somewhere it's there. Okay. Any questions about this? Is this making sense? Can I erase this? Because once I erase these images, I can't get them back. Do you have any questions about them? Okay,
Yeah.
no. So let me erase both of these, right? Clear. Going, gone. All right, so let's get back to, so in order to test for biconnectivity, all we're going to do is test whether there's any articulation point. If there are no articulation points, we are done because the graph must be biconnected. And last time we talked a little bit about how we're going to test for articulation points. It turns out that an articulation point is relatively easy to check, and so is it to check whether there is a bridge. And both of these are related to this depth first search that we're going to do. This is the claim that we're making, that is a graph. If a graph is not biconnected, it must have at least one articulation point. If there are none, it must be biconnected. So we're going to use depth first search, and we're going to use something called low numbers. And I'll see if I can explain this to you. Yeah, in fact, I better go back to the previous picture here. Yeah, this one here. Yeah. So it turns out that, by the way, before I show you this example, what are the biconnected components of this graph on the left? How many biconnected? Is it biconnected? Let me ask you the first question.
The whole thing, no.
No.
No,
The whole thing is not, right? Is it connected?
Yes.
Yes, it is. Is it biconnected? The answer is no. That means that there must be biconnected components. And remember, a biconnected component is very nice in the sense that between any pair of vertices, you should be able to have two disjoint paths. Now, how many biconnected components you think this has?
let me see. 1, 2, 3.
4? No, 5.
Close, but no cigar.
Let's see.
Oh, maybe 7. A, F, D, E, C, G is 1.
Okay, good.
Right?
Very good.
Oh, it's
Yes.
8 because it's A, G, D, E. Oh no, A, G, E, D, F. Right, that's 1. F, E,
No,
G, C,
it will
A.
also have C. No, the C and D are part of that same one.
Oh, okay.
Is
so
G,
it's
J,
how many cycles
L,
there are?
It's
Is,
not cycles. Don't just go on cycles. That's a wrong concept to have.
Oh,
A cycle is just a simple degenerate form of a biconnected component. If you have a cycle and if you have some extra edges, it's still biconnected, the whole thing.
oh, okay.
Okay.
Wait,
So
can we,
go ahead.
the way I was doing it is I was looking at the DFS tree here on the right.
Yeah.
And since we know it's an articulation point, if for one vertex, the subtree must have one vertex in a subtree must have a back edge be above that vertex.
Correct.
So we can do it completely off of that, right?
All right. So let's start then with which are the articulation points? That's an easier question to ask.
G is one of them.
G is 1, obviously, because you remove G, the whole thing breaks up right there. Yeah. What else?
A.
A, because why? Because
Yep.
B falls apart,
Mhm.
right? Okay, great. What else?
J.
J, because K falls apart. Yes, that's so we've identified 3 now. Yeah.
And H as well.
And H. So 4 articulation points. Good. That's actually precise. That's correct. Now, that doesn't mean that there are only 5 biconnected components. You have to kind of go through the because some articulation points might end up making multiple pieces. And in fact, G, if you remove G,
Oh, yeah.
it makes 3 pieces, not just 2. All right. So you have to be a little more careful with the biconnected components. So do you know what they are now? So let's first get the easy ones. AB, this is just a simple edge and it's a biconnected component, right?
Mhm.
JK is a simple biconnected component, right?
Yeah.
What else? Easy ones.
HI is a simple biconnected component.
HI is a simple one. What else? So it turns out GH is also a biconnected component by itself.
Does that mean AG as well, and GJ and GE?
No, AG
Okay.
is not, because it's part of a cycle.
Okay.
GH is not part of a cycle. Right?
So if an
Yeah.
edge is not part of a cycle, that could be considered an a biconnected component.
That's actually called a bridge.
Oh, it's a bridge.
By
Yeah,
our
it's a
definition
bridge.
from last time, right?
A bridge, yeah,
Yeah.
a bridge.
Yeah,
Bridges
and
are-
in fact, both ends of the bridge it turns out that they are articulation points.
Yeah, it makes sense.
Yeah. Okay.
So over here, this is a bridge, this is a bridge, this is a bridge, and this is a bridge. The articulation points are A, G, H, J. Those are your articulation points. So your biconnected components turns out to be this whole piece over here, except for B. Because you can go from A to C to G, D, E, D, F, and all of this forms a cycle. So all of this is part of one connected component, a biconnected component, I mean. AB is another one, that's number 2. Then GH is the third one, HI is the fourth one, JK is the fifth one, and this whole piece is the sixth one.
Wow.
That's G, J, L, and M. Did you get that?
Yeah.
And it turns out that you can figure that out even from the picture on the right. So let's see how we can figure that out. Now, AB there are no back edges going. So clearly this is a bridge and this is a biconnected component in itself. Same is true of HI and same is true of JK, right?
Right.
So those guys, you can remove them and you know that those were biconnected components. Well, it turns out that when you removed HI, you also got a new one here, that's GH. That's also going to be a biconnected component and you can remove that. So there are 4 trivial biconnected components that are just simple edges. Now we're left with something much more interesting. So remember, let's remove K, let's remove H and I, let's remove B. Now take a look at what you have and see if you can understand the pattern here. What you'll see is that because G is a articulation point, right? Because G is an articulation point, everything on this side is part of one connected component. So that's A, G, C, along with E, F, all of the, and D. All of these are part of one biconnected component, except for B. Is that clear?
Yeah.
And same thing over here, G, L, J, M. All of these are part of one biconnected component, not K and not H or I, but the rest over here. So you get two big biconnected components. One is over here, one is over here, and then there are a few hangers on the trivial ones, A, B, J, K, G, H, and H, I. That's what you get. Now, we're going to try and write an algorithm that is able to figure this out for us. And it turns out all of this comes from very similar arguments like what we did with the articulation points. And you can see that over here. Remember that, let's start down here. J is an articulation point because from this subtree, you don't have a back edge going up, right? But this side is fine because there is a back edge going out, but from this branch, you don't have a back edge that goes up. So therefore, J is an articulation point. And you can remove this part and it'll be a biconnected component. Now, when you get here, again, this part is a biconnected component and you can remove this and you'll be left with this guy here, which is also another biconnected component. You'll remove that. You won't be able to remove this, but it turns out that this entire branch over here does not have a back edge that goes beyond G. If there was a back edge that went from L to E or L to F or L to A or J to A, then G would not be an articulation point and everything would work out. But since G is an articulation point, everything underneath it, after you've removed H, I, and K, are now going to be one biconnected component. Once you do that, what are you left with? You're left with this piece here. And again, over here, A to B can be removed because that's a biconnected component. Then you'll be left with A, F, E, D, G, C. And you'll see that this whole thing has back edges going up here, back edges going up here, back edges going up here. So that whole thing is biconnected and you can leave it as it is. And you want an algorithm that reports all of this. And we're going to use simple constraints to check for articulation points. If we don't find an articulation point in whatever we are left with, that's going to be a biconnected piece and we can report that. So let me jump straight to the algorithm, which turns out to be a version of depth first search. So you see that this is just depth first search rewritten. You have the moment you visit a vertex, you color it gray, you increment the time, you set the depth first search number, and then you look at every adjacent vertex. And if necessary, if that vertex is white in color, you make a recursive call for DFS starting from that vertex. When you're done with all the adjacent guys, you come back out, color it black, and set the finish time, and you stop. Now, this is standard depth first search. Now we're going to see how to modify it to take care of biconnected components. And it turns out that the basic structure is exactly the same. When you start, you go and color the vertex gray. And then there is this for loop that does something for every vertex that's adjacent to it. And then if the color of the edge that you see is white, sorry, color of the other vertex is white, then you recursively call depth first search visit over here. Here we're going to call this BCC recursively. So the basic structure remains the same. We're going to add a couple of bells and whistles to this. And you see that we are going to, so the moment we get to a vertex, we're going to initialize a new variable called the low number. And this low number tells you how far up the tree there is a back edge that you can get to from one of the descendants. And to start with, it's going to be set at the depth first search number, but it'll get incremented or changed as you go along. So this stuff in orange helps you to report a bi-connected component. We'll skip that to the end. But this is the important part here. It says that if the low value of a vertex is greater than or equal to its depth first search number, then that vertex is an articulation point, which is the same as saying that if there is a descendant from which I can go all the way above the vertex u, then I can reach a depth first search number that's lower than that of u, then this condition gets satisfied. Will not be satisfied, and u will not be an articulation point. On the other hand, if there is no such package, then u is an articulation point, and you can report it. And there is, you'll have to kind of go back and look at this to understand it. It'll take some time. I'm going to let you do that at home. One thing that's important is when you finish with a subtree, you have to update the value of low with the new low value. And there is this part of the code is actually really, really nicely written. It's not written by me, it's written by someone else. But it computes the bi-connected components in a really, really nice manner. Unfortunately, we don't have time to go through this in gory detail, but I would like for you to go and stare at this and work it out with an example, maybe work it out with the same example that I showed you, and see if you can understand all the pieces here. But it's intricate, but it works, and it works well. Can I answer any questions for you guys?
What's the similarity between this and strongly connected components?
Yeah, so strongly connected components is the version of bi-connected components, but for directed graphs.
Ah, okay.
And it's a little more complicated. We'll talk about that some other day. It's less interesting, but I'm happy to talk about it if there is an interest.
Really quickly, could you possibly think of like a real life application of
Oh
this
yeah,
theory?
heck yes, yeah. So articulation points are extremely important. So if you go back to this example, this is like saying, if this is my road network, where are my weak points? And you see that G is a serious weak point, because if something happens here, think of this as a computer network or a road network. If this were a computer network and this computer goes down, what happens? Your network is not connected anymore. So articulation points are important. So when you look at a network, you want to understand, hey, are there weak points here? Or can you always find alternate ways of getting from somewhere to somewhere else? So if you have two disjoint paths between every pair of vertices, we called it biconnected, but really what we are saying is it's fault tolerant, meaning if some computer goes down along the way, no problem, I'll find some other route for you, because there are always two disjoint paths. Does that make sense?
Yeah, that makes sense.
So your messages will always get through, okay, in a computer network, if it's biconnected. So that's where it's important. So it's a stronger version of connectivity. In connectivity, all we were concerned about was, hey, can I get from anywhere to anywhere? Yeah, all that's good. But if you have some weak links, it could hurt you. So biconnectivity takes you to that next level and says, okay, even if there is a failure somewhere, no problem, I can still get from anywhere to anywhere. Now, there is also a concept of triconnectivity, where you can have two failures and you're still able to get from anywhere to anywhere. And that also, there's a complicated algorithm for it that's based on depth first search. You can also do something called K connectivity, where you can tolerate up to K-1 failures. So all of these are extremely important in network research. People who work for AT&T or Akamai networks or something like this, they would really need to understand this in order to get things to work well. Other questions? Was that convincing enough for you, Clement?
That was very convincing.
Okay. Any other questions? So I'm going to stop here and let you have a good long weekend.
Thank you, Professor.
All right.
Thank you, Professor.
My pleasure. Yeah.
Thank you, Professor.
Okay.
Have a good weekend.
You too. You too. Yeah. Stay safe.
Dr.